Assalamualaikum and welcome everyone. Now we have finally made it to chapter 10, Applications of Differentiation. 10.1 Extremum Problems. The learning outcomes are: the first one is to find the critical points, the second one is to find the relative extremum using the first derivative test, the third one to find the relative extremum using the second derivative test, and the fourth one to solve optimization problems. 10.1.1 Critical points and stationary points. A critical number for fx is any value of x or the x coordinate in the domain of fx at which the first derivative of fx is equal to 0 or is undefined, whereby a critical value for fx is any value of y, and the critical point where the first derivative of fx is equal to 0 is called the stationary point, and the value of the function at that point is called the stationary value. Now let's have a look at graph examples for which the first derivative of fx is undefined. The first graph that we have here is a quadratic graph. What we can see here is the orange line goes through the stationary point of the graph, and C here represents the critical number for the graph. The next example involves a cubic graph. Same here. We can see that the orange line goes through the stationary point of the graph, and C represents the critical number for the fx. Now let's have a look at graph examples for which the first derivative of fx is undefined. So at the asymptote for the first graph, the first derivative of fx is undefined. Therefore, C here represents the critical value where the first derivative of fx is undefined. Now the second graph involves a cubic graph. So we can see here that the orange line goes through the critical point of the graph or the stationary point of the graph, and C here represents the critical number for that graph. The third example involves a straight line graph which is reflected upon the x-axis. So the orange line goes through the stationary point of the graph, and C here represents the critical number for the graph. Now we have come to example 1, question number 1. Find the stationary points and stationary values of the function fx equals 2x cubed plus x squared minus 20x plus 5. From our lesson, we know that at a stationary point, the value of the first derivative of fx or f prime x is equal to 0. So in order to find the value of x at that stationary point, we need to first find the first derivative of fx, which is equal to 6x squared plus 2x minus 20. And we know that f prime x is equal to 0. Therefore, we can equate 6x squared plus 2x minus 20 to 0. In order to solve that, we can first simplify. So we get 3x squared plus x minus 10 equal to 0. And then we can factorize. So we get 3x minus 5 times x plus 2 equal to 0. So the first value of x is 3x minus 5 equals 0. So x is equal to 5 over 3. And the second value of x is equal to negative 2. Thus, in order to find the y-coordinate or the value of fx when x is equal to 5 over 3, we need to plug in the value of x equals 5 over 3 into fx. So when x is equal to 5 over 3, fx is equal to 2 times 5 over 3 cubed plus 5 over 3 squared minus 20 times 5 over 3 plus 5, which is equal to negative 440 over 27. And when x is equal to negative 2, fx is equal to 2 times negative 2 cubed plus negative 2 squared minus 20 times negative 2 plus 5, which is equal to 33. So from all the values that we have obtained now, we can conclude that the stationary points are (5/3), negative 440 over 27, and negative 233. And the stationary values are negative 440 over 27 and 33. So that's all for example 1, question number 1. And now let's move on to example number 1, question number 2.